You are only given that V and W are finite dimensional. If I'm not wrong, right?
Yes, sir.
And you have to prove that this is a finite dimensional vector space.
Oh, so we have to prove. Wait, what?
I'm not sure that with the additional multiplication, define inclusion is a finite dimensional vector space.
So isn't VW a linear transformation?
No. Hom VW is the set of all linear transformations.
So how can a linear transformation be a vector space?
Wait. So it is a set of linear transformations from V to W. It is not a single linear transformation. So the picture is something like this. You had a vector space V, you had a vector space W. Okay? And then you are taking all possible linear transformations from here to here. This collection this collection is Hom VW. So Hom VW is neither any one of these blue arrows. It is the set of all these blue arrows that make this set. Is it clear now?
Yes, sir, but I still don't understand how that can be a vector space. Because it's a linear transformation. It transforms what's in V to what's in W.
Yes, correct. But now, the next thing is, what is a vector space? A vector space is a set. So firstly, I have a set. This is a set. Okay? Then there needs to be an addition. We call it the addition of vectors, which is actually a binary operation on that set. There needs to be a scalar multiplication. What does it mean? It means it's a map and these two need to satisfy certain axioms which we said in the beginning, right? Okay? Now comes this is the first part of the definition. And then certain axioms. So for instance, the addition has to be commutative. There has to be a zero for this addition. The addition has to be commutative and associative. There has to be a zero for this addition. There has to be a negative or inverse for this operation, right? And the scalar multiplication must distribute over addition and so on and so forth. All those conditions, right? Now, the next part comes in how are these. So, if I take a pair of homomorphisms, I am supposed to give you a homomorphism here. That means, this is the next part of the story. In the first part, f plus g must itself be a map, must be a function from V to W. And that's the second part of the definition. And similarly, this lambda f must be a function okay? So now things are getting clearer, but it's just a function.
So like you do this the way you would normally prove a vector space. You just say that f and g are elements of Hom VW.
Yes. Yes.
Oh, okay,
Exactly.
okay. I understand. So, and how would you go about showing that the dimensions of Hom VW are equals to Mn?
Yes. So now you know that Hom VW is a vector space by itself, and on the other hand, sorry. So now I am assuming that the dimension of V is M, dimension of W is N, B is a basis, and okay? And then you have done lots of things. There is a map over here, which gives you the matrix of a linear transformation with respect to the basis.
So can we please just go back one step? Oh, no. Like, can you, just the step above, could you re-explain it, please?
Okay. So I'm just saying you have just discovered that Hom VW is a vector space. Okay?
Mm-hmm.
And you know that the collection of all matrices of, this I meant something else, 1 minute. The collection of all matrices, so since this is this, the collection of all matrices of order n cross m, where n is the dimension of the codomain W, M is the dimension of the domain V, okay? So the collection of all n cross m matrices with real entries, with usual
So you're going too fast.
Which one?
Can you just say the last sentence again?
Yes. The collection of all n cross m matrices with real numbers
With real numbers
as entries
Oh, yes.
is a vector space by itself with matrix addition and matrix scalar multiplication as the operations, right?
Mm-hmm.
And then you have also put forward that if you give me any linear transformation f, there is a unique matrix which is exactly this one. You take the coordinates with respect to C of f of V1. So that's the first column. And the nth column being this. So this is this matrix. And you have already shown that matrix, this map, F going to this matrix, we have shown that this is a bijection. Okay? Well, that was all that we did in the first place. We showed that for any matrix, we can get hold of a linear transformation from V to W, whose matrix is that. Okay?
Yes, sir.
And that linear so for each matrix there exists a unique linear transformation whose matrix is that given one. So that tells us this association of putting F to matrix of F is a bijection. So we have shown that matrix
so something's wrong with the sound. We can't hear properly. Sir, I can't hear you. I don't know what's going on with the sound.
Please mute your microphones. Mute your microphones. Okay, so we have shown that this is a bijection already. Now in this problem that you are saying, you are asked to show exactly that this is a linear transformation.
So weren't we showing that Hom VW is a... Oh, but that would... Oh, yeah, okay.
So it follows that this is a bijection linear transformation. And hence, so this is also something which we did, that if V is finite dimensional and there exists a bijective linear transformation from V to W, then W is also finite dimension and the dimensions are same. So,
okay, so how to answer this question is that you need to show that the matrix B to C is a bijection and it is a linear transformation. And because V and W are finite dimensional, this would imply that the dimensions of Hom VW are equal to Mn.
yes. Yes, exactly.
So is it necessary to prove that the dimension of the Hom VWN is equal to the dimension of the...
This follows from these two statements, right?
Wait.
Okay. Yes? Okay. Yes.
Sir, how are you?
Yes, I'm fine. How are you?
I'm not good.
My goodness, why?
The time that you have allocated for this lecture from 4 to 7 p.m., some of us cannot find transport to go home. 6 was better.
Yes, but you see, I had no other option than this. So, I had to. There was no other way. At least something is better than nothing. So you can at least get the copy of the lectures at least. Yes, next. So next. Okay. So now let's carry on with last time with the load shedding and so on. Many things fell through the cracks, and I also made a mistake near the end. So let's actually redo this eigenvalues business.
So I got lost. Can you understand?
Huh?
I said I got lost last week.
Yeah.
Couldn't get you.
Okay. So the two things that I need is, the first one is about these linear transformations. So actually what we have shown that this and this are isomorphic, and this actually tells us, this statement therefore means oops. Apart from this, we also proved another fact over here, is that if we had another vector space, say, so if we had three vector spaces, say the dimensions, as I said, is M, N, and this one is P, and we had linear transformations like this, and we had basis over here, the basis is B, says C and D, then we have also shown in those problems that B to D okay? This was also shown. Good. Now, we want to look into square matrices. So that means we want to look into Hom VV. So on this side, and we have taken the basis B over here, and so on this side it is GLN, which I was writing, the square matrices. Now, as vector spaces again, these are same. So these are isomorphic as vector spaces. But there is yet another structure over here, and there is some, that is a multiplication. What is it? Over here, you have addition of matrices, scalar multiplication of matrices, as well as multiplication of matrices. And the multiplication says,
Sorry, sir.
yes?
We can't actually see where you are writing. There's a small screen which is blocking everything on that side. Just after
Which side?
Just after the arrow. The arrow, yeah.
Oh, it's definitely not on my side. Let me ask the person. 1 minute. What's his name? Thabo.
Yes, sir. I'm here.
Yeah. Thabo, they are saying that there is some obstruction on the screen on their side.
Where?
Yes. Which person? Yeah.
We're seeing the cameras.
7?
Yeah.
Is that you who's got a problem?
Yes, we're seeing the cameras on the screen, and it's blocking the view where the lecturer is writing. Yeah.
Oh, okay. Just give me a minute. Let me just see first.
Why the lecture was changed? Why the
So venue was booked.
Okay, Devin, just tell me what's happening on your screen.
Nothing at the moment. You just minimized it.
Okay.
Yeah, that's fine.
Okay, cool. You can continue, sir.
Okay, thank you. So now you see we have this multiplication of matrices as a third operation over here, and moreover we know that the addition of matrices is associative, is commutative. We have this, it's a vector space, but the multiplication also is associative, and the multiplication distributes over the addition from both sides. This is something which we know from our previous course, possibly of operations with matrices. Okay? So this happens. So you see, the square matrices is just not a vector space. It has some more structure, right? And the structure is of a multiplication which distributes over addition from both sides. Why I need the both sides? Because the multiplication is not commutative. So saying one of them doesn't give me the other. Okay? And further, there is this identity matrix which when multiplied from either side gives me back that matrix. Okay? And as expected on this side also, we have obviously the addition of homomorphisms, the scalar multiplication as we have seen, which makes it a vector space and so on. But we have another kind of a multiplication, which is composition of since everything is from V to V, F and G are linear transformations. Forces F compose G ought to be also a linear transformation from V to V. Yeah? And this composite distributes over you can check this. So this was one thing which I asked you to check. Okay? So it also distributes from both sides. Again, the composition is not necessarily commutative. And we have this specific identity linear transformation over here, which
So the one V means an identity.
Yes, it means the identity linear transformation. Okay? And Now since we are taking only one basis, right, on both sides, we'll just write MAT instead of MAT B to B. Okay? So, the multiplicative law which we had here now gets much more simplified as yes?
Just a question. But when we write composition of G and F, isn't it like G of F, where
Yes.
F is inside of G?
Yes, exactly.
So
first you do F. So here I meant that you first do F and then follow it by G. Yeah? So you read from the other side, not like English, like Urdu, right? Okay. So MAT now is not only a vector space isomorphism, or it's not a bijective linear transformation, but it also preserves the multiplication. Good. Now let's see some new things about this. So we can have a matrix, multiply it with itself, and so on. Right? Similarly, if we start off with and why do I stop here? Okay, I can start off with a linear transformation. Please, why did I stop here? I could even have had a to the power 0, which I defined to be my identity, and over here f to the power 0, which I defined to be the identity linear transformation again. See, what I am doing, underline, the matrix of identity linear transformation is this I, matrix of f is A, as if, okay, matrix of f squared is matrix of, yes, A squared, right? So the matrix is actually telling us what to do. Okay? So while this is true, we can also then speak about, therefore, things like this. Right? So we can also speak about things like this. Right? So in general, if you give me a polynomial, we can speak about P of f, which is A0 times 1v, we can speak about the polynomial in the matrix A, which is A0 times I.
So the coefficient of the polynomial,
they are real.
By the f, okay.
So that's playing the role of the scalar multiples. Right? Okay? So as if I'm just replacing this x by either f or a. Okay? Just remember, PF is still a linear transformation and PA is still a matrix. Okay? All right. Next we would require something special about complex numbers. Which are numbers which are written in this form a plus ib, where a and b are real and I square is -1, and I believe you know what is its conjugate. It is a minus ib. A is often called the real part of z. B is often called the imaginary part of z. Okay? And so on. Okay? So you know that, and you also possibly know that bar square is z bar, and this is usually called the modulus of this complex number and so on, right? Okay. What I require about complex numbers is this very, very important theorem. It is called the fundamental theorem. And what does it say? Every complex polynomial, or every polynomial that means okay, and as a consequence,
Just the question says, so you wrote that every polynomial is an element to complex numbers.
no, remember Rx, remember this symbol? This was the set of all polynomials in X with coefficients being reals, right? So similarly this is the polynomials in X with coefficients being complex numbers. Okay? All right. What are the consequences? The first one, every has so every polynomial has a degree. it has exactly as many roots as its degree. So every nth degree polynomial has exactly n complex roots. Okay? So that is a beautiful follow-up of this fundamental theorem. Okay? It is fundamental because it has several implications, and it's one of the most important properties of complex numbers. Okay. We will use, last time I gave proofs of this, but today I will not. If if I take a real polynomial and if I take a real polynomial and there is a complex root alpha of it, then the conjugate of alpha is also a root of it. So we often say it as follows: every real polynomial has roots in conjugate pairs. Okay? If alpha is a root, so saying again the statement in B, if I take a polynomial with real coefficients and manage to find a root alpha, which is a complex number, then its conjugate alpha bar will also be a root. Okay? Remember, this is only true when the coefficients are real. When just now, for instance, here is an example. Suppose you take PZ. This is nothing else but z minus I square. And its roots are therefore only I and I. Okay? But its roots are...
It's z squared minus 2i.
2iz.
2iz.
Okay? So, something is important about this R over here. So it says that if, yes?
What's the conjugate?
If Z is A plus IB, its conjugate is A minus IB. Okay?
Excuse me?
If Z is A plus IB, then its conjugate is A minus IB.
Oh, okay.
Okay? So, there's a very important fact. It says that every polynomial with real coefficients, therefore, has its roots in conjugate pairs. Okay? And therefore, what happens is that if you have a odd degree polynomial, okay, and then go on pairing odd degree polynomial with real coefficients, okay, you go on pairing, so one will be left out, right? So that is the conjugate of itself, right? And hence that must be a real number. Okay? So in particular, okay? And what about for even roots? So of even degree.
Sir,
Yes?
why is this true specifically when the degree is odd?
It just follows from me. Listen again, I'm saying. Since you can pair off now the roots of a real polynomial, you can pair them off. You take a root and take its conjugate.
Okay. Okay, I see now.
Yeah. Okay? So what did I do? Sorry. Okay. So therefore, so this is the basic thing that we'll require. Okay? So now let's come back. How do I apply this? So the first one is, suppose now my basic setup is always this. Okay? Now suppose I have a linear transformation. Let me take a V from V, or choose and fix over here, so that V0 is not equal to 0. Then consider this list. This is obviously, what can you say about this list? No, this is a list. What binomial? How many vectors are here?
Vectors.
Yes?
N vectors.
N?
N vectors.
There are n vectors? Why?
So they're n plus 1 vectors.
There are n plus 1 vectors. 1, 2, 3. So n plus 1.
Oh, N plus 1.
So therefore is linearly dependent or independent?
Independent.
Why? I have told you the dimension of V is n, and you have taken n plus 1 vectors. Can it be linearly independent? Yes, it's linearly dependent. And hence, there exists sorry. Okay? But then now using my yes?
Why should we multiply that lambda 01V lambda T by VO?
Which one?
The second last line.
This one?
Yes, sir.
Remember, as I said, this one is also a linear transformation, right? And that, how do I get it? What is its value at V0? It will be alpha 0 at 1V of V0, which is V0, alpha 1 of T of V0, alpha 2 of T squared V0, and so on, up to alpha n of T to the power n V0. So, this line which you saw just above is nothing else but the value, the left hand side is the value of this linear transformation at V0.
Oh, okay.
That was the definition, right? So this at least we can say. Okay? So now I don't know about this. What is this? N, I don't know. But however, immediately I can say if n is odd, then I know there is a real root. Okay? But in general, I cannot say anything. Okay? So for instance, so from here, we cannot come anything, but we can show that suppose let n be 2, okay? And let me take V to be R2. And let me take my T so what shall I do? Let me just think. So obviously a linear transformation, but indeed this cannot have this. So what is the P for this? Okay, let's see. So let me take, for instance, any xy. Then I'll try to do this. So I'll have alpha 0 xy plus alpha 1 t of xy okay, this must be 0. I'm trying to find out this alpha 0, right? So this I know. Remember, how do you get t? You just interchange the coordinates and put a minus, right? So this is okay. So this is coming to this. So what do I have about alpha 0 plus alpha 2 minus? Sorry. So it is alpha 0. What do I do with this? Alpha 0x plus alpha 1x plus alpha 1 minus alpha 2 times x is 0, as well as alpha 0 minus alpha 1 minus alpha 2 times y is 0. Right?
Also, you separated it.
Yes. So you see, from here I will get hold alpha 1 and alpha 2. Okay? So for instance, if I took both x and y to be non-zero, then I will get alpha 1 minus alpha 2 is minus alpha 0 and alpha so in particular alpha 0 and alpha 1 minus alpha 2 minus 1 is alpha 0. Okay? So from here you get alpha 2 is equal to alpha 0, from which you get alpha 1 to be 0. Yeah?
Could you please explain how we got the alpha 1 plus alpha 2 is equal to alpha 0?
Well, if you take, so you have these two equations, right? Now if x is non-zero, if you assume now that because I took this.
Oh, okay.
So if you assume both x and y to be non-zero, from here you should get, from the first one should give you alpha 1 minus alpha 2 is minus alpha 0, right? And the second one should give you alpha 1 plus alpha 2 is alpha 0. That's what I got. Okay, so alpha 1 becomes 0 immediately.
So isn't it alpha 1 minus alpha 2 is equal to 0?
It's not 0. Alpha 1 minus alpha 2 is minus alpha 0.
Oh, and then you swap them. Okay.
Okay, so alpha 1 becomes 0. and then it becomes that alpha 2 and alpha 0 is equal to 0. So from here you will see that you will get some specific values of alpha 2 and alpha 1. So you will see that, so if you carry on a little bit, you will see that the matrix of T with respect to the usual coordinates, it looks like this. Okay? So, and this one, and there is no and what becomes of your P? What becomes of your P? Alpha 0 is equal to alpha 2. Okay? And so, yes, alpha 1 is 0. So, clear? On the other hand, suppose so then you can write please close the microphone from the other side. Okay? So this tells us therefore, right? Remember, this multiplication means it's actually composition. Right? Okay. Now, it turns out, yes.
I still don't understand why we specifically use T minus lambda 1V.
Remember? Right?
Yes, sir?
So remember how was I A0? This gave me this polynomial linear transformation. Okay? So whenever you have just a scalar, to make it a linear transformation, it's a scalar multiply with the identity. Okay? This was the scalar. It became the scalar multiple of the identity. Right? Over here, it was the scalar multiple of the identity. Okay?
Yes,
All
sir.
right. So now let's go back. So since you have told me that PT Okay? And let me write it in this way, okay? Then, well, I'm just driving to some place, so I'm a little bit not rigorous here. I'm saying also assume that q lambda is not equal to 0. Okay? That means lambda is not a root of this remainder. Okay?
Oh, okay. So you want to write q of x not equal to 0.
Q lambda.
Q lambda.
Right? That means lambda is no more a root of q.
But lambda is a
Okay?
real number.
So then it will follow okay? So what does this mean? It means that all right? Okay? Now, so this is what I want, this is the exact picture which I want to capture. What is it doing? So V0 is a non-zero. So if I look into this kind of a solution, this kind of an equation, I'm trying to say that V0 is a non-zero solution of this equation, right? Okay, so that brings us to the definition. Right? By saying that this, I mean to say that there exists a non-zero solution, right? There exists a non-zero V such that this will vanish, right? So that's exactly what I was doing here. There exists a non-zero V which makes this to vanish. Okay? So in such a case, we will say that lambda, if you can find, so t is given, right? If you can find a lambda, real number, such that the kernel of this is non-zero, right? In that situation only, we will say that lambda is an eigenvalue of t. Okay? Non-zero. Okay? So all the non-zero and this one the kernel of this. This is called the eigenspace. And an alternative symbol for this eigenspace is this. Okay? Since we know that there is this parallel with these matrices.
Did he teach you about canals?
The parallel with matrices, so this is the other side of the story, therefore.
So what's written in red?
That's the
Yes.
right.
This is called capital Xi. The small xi looks like this. The capital Xi looks like this. It's a Greek letter. It's the Greek E. So E for the eigenspace. This is that eigenvalue lambda and in brackets T. Okay?
So it's just E at T.
Yes. But we usually don't use the Latin E, we use the Greek one.
Oh, Xi.
Yeah. Okay?
Just the question says, what does the G stand for?
General linear group.
Oh, general linear group.
Yeah. So, such an X and over here so this is called the eigenspace. Okay, so these are the parallel definitions. You can see that lambda is an eigenvalue of T if and only if it is an eigenvalue of the corresponding matrix. Okay, so these are actually that matrix map is a translator from one side to another. Okay. Okay. All right. Now the question comes, who is this? Whose microphone is this? Well, if you don't mute it off, then I'll have to mute it from this side. So now how do you compute? So we'll go back to matrices. Since we saw this, now we come back to matrices. And so how do you compute the eigenvalues then?